This video describes one of the newest and most unusual features of Tidewater Planetarium, the ability for users to add their own planet to the model of the solar system and see it displayed in Tidewater Planetarium's views. The inspiration for adding this feature was discussion among astronomers about the possibility of a ninth planet in a very unusual orbit as yet undiscovered by science. We thought it would be interesting to be able to allow people to model a planet like that as it's discussed by astronomers. But there's a better reason for adding this feature to the program. If you're a student of astronomy and you're learning about how astronomers describe and discuss the orbits of planets, the parameters and terms that are used are very non-intuitive. It's hard to visualize what those parameters might mean, at least it is for most of us. And we thought by allowing a user to create and adjust the parameters of an orbit and see what happens to that orbit, it would make it a lot easier to understand what those parameters mean. So let's take a look at this view. This is called the Solar System view in Tidewater Planetarium. It's looking at the objects in the solar system from out in space. We can display the names of objects like Earth. We can turn their orbits, displays of their orbits on or off to clutter or declutter the image. We can change our direction of view by holding down the mouse button, in this case the left mouse button, and dragging the cursor, and that will tip the display so we can look from above or below the plane of the Earth's orbit, called the ecliptic plane, and we can rotate the view to look from any angle. The right mouse button does the same thing, but with a finer control. We can also zoom in and out to look at the inner planets like Mercury here, or the outer planets like Jupiter. The other planet displays are turned off right now orbit displays are turned off right now to give us a less cluttered view. So those are the basic controls for this view. They're very important to being able to look at a new orbit that you're creating and understand what it's really going to be like. We can click on a control button here. It's called Add Planet, and it's also available in the Edit menu. When we click on it, we get a dialog box with lots of parameters that define a new planet, and we get a view of an orbit with the default parameters. There are two categories. The top category of parameters define the planet itself, its name, the mass of the planet, its diameter, the reflectivity, which is how much of the light that hits the planet is going to bounce off and be re-radiated into space, and the display color used for things like the Earth blue, Mercury yellow views in Tidewater Planetarium. Below, we see the parameters of the orbit itself. So we'll describe each one of those, but first let's look at this display to see what we're seeing here. The teal ellipse represents the orbit described by these parameters. The gray, similar looking ellipse is that same orbit but rotated down flat into the Earth's plane of rotation around the Sun, the ecliptic plane. And by showing both of these two, the reference gray orbit and the actual teal representation of our planet's orbit, it's a lot easier to visualize what's going on with this new teal colored orbit. The first parameter we're going to describe is called the longitude of the ascending node. Obviously not a term that people are familiar with, but what it is the ascending node of an orbit is where a planet or an object in that orbit will pass from below the ecliptic plane to above the ecliptic plane, so to the northern direction above the Earth's plane of orbit from the south. That point right now is right where this red line crosses our teal orbit, and so that's the point of definition. The angle, longitude of the ascending node in degrees, is the distance in degrees from this reference direction, it's called the vernal equinox, to that point of the ascending node. Right now it's 0 degrees of separation because they're in the same place, but as we increase it, we'll see the um, angle highlighted in yellow, and we can see that it's the angular distance in the reference plane from the vernal equinox to this point called the ascending node. If we zoom out a little and see what that looks like as we increase, rapidly increase the parameter, it's as if the teal orbit were being rotated on a spit on this north to south, up to down axis perpendicular with the ecliptic plane. So that's a key parameter describing orbits. When we, and let's get that at a little bit of an angle, we'll leave it at 20 degrees. When we're adjusting that parameter, we get this angle highlighted, but when we switch to another parameter, the highlighting will change or disappear. So the next parameter is called the argument of periapsis. The argument of periapsis is another angle, and that is the angle from the longitude of the ascending node, this reference direction here, to the point on the orbit where the object will come closest to its focus of orbit, in this case the Sun. So the periapsis is this point right here. The periapsis distance is the distance between them. And the angle, the argument of periapsis, we'll see, is the measure from the ascending node to the periapsis in degrees in this case. Sometimes you'll see it in radians as well. Omega is the Greek symbol to represent the argument of periapsis, and here it's displayed as 80 degrees. So as we change that parameter, we'll see that what our orbit is doing, it's keeping the same shape, but it's once again rotating like it's on a spit. But this time the spit is actually perpendicular to our new orbit, not perpendicular to the ecliptic plane like the longitude of the ascending node's rotation. So we're able to rotate the orbit in another direction, and this is how astronomers define that second term of an orbit. The third parameter is a little more familiar to us. It's called inclination. And as we adjust that, you'll instantly see what it is. It's the angle between the reference plane and the actual plane of our orbit. And we can adjust that to whatever we like. The fourth parameter is similarly fairly simple. It's called the semi-major axis. And the semi-major axis is half the distance along the longest point of our longest axis of our ellipse. It's half that distance from the very center to either extreme. So a simpler way to describe that would be bigger, smaller. As we add, we make our orbit bigger or smaller, but we keep the shape and the orientation the same. And the final major parameter of an orbit is called eccentricity. That's how elliptical the orbit is. So if we reduce the ellipticalness of our orbit all the way down to 0, we get a perfect circle. And it takes a few clicks to get down there. Or we can set it to a relatively high value. We can type in the box and do that, and there's 0.7. If we increase it even more, we see that the orbit becomes extremely elliptical, but keeps the same semi-major axis distance. And if we zoom in, we can see that our orbit is getting to the point where it's very thin indeed. And as we do that, we see that the object's periapsis distance is getting smaller. So like a comet that sweeps in extremely close to the Sun and then whips way back out into space, a highly elliptical orbit is thin and relatively long compared with its width. That's all of the parameters to define a standard elliptical orbit, also called a Kepler orbit after Johannes Kepler, who first proposed that the planets in our solar system were in elliptical orbits rather than circular orbits, which was a radical proposal at the time. The final parameter, though, we see down here is called mean anomaly. And mean anomaly doesn't change the orbit, it changes where the planet is on the orbit. And so at a particular time, in this case, this date and time, if we adjust the mean anomaly, we're adjusting where the planet is going to be on the orbit from this point forward. So if we're satisfied with that, we can save it. But before we do that, I'm going to suggest that we adjust our orbit. We make it pretty round. So let's set the eccentricity at about 0.1. So that's a pretty round orbit. And let's put it out here between Jupiter and Mars in size. So let's increase the semi-major axis until it gets big enough to basically be out, between those two. And we could also tip it down so it would be more like a typical planet orbiting close to the a zero incline to Earth's orbit. But instead, let's do the opposite and increase the inclination, because that's been one proposal for where this undiscovered ninth planet might actually be. So let's give it a high inclination. And then let's move the planet up so at the present time it'll be up close to the highest, instead let's put it down at the lowest extent below the ecliptic plane. So there's about as far below the ecliptic plane as it's going to get. And then I think that's satisfactory. We can adjust, of course, the rotate around the periapsis position, and we can rotate around the longitude of the ascending node, but this is a pretty good orientation. So let's save it there. First, let's though give it a name. Let's call it Planet X, because that's the way people have been referring to this hypothetical planet. And when we hit save, there it is. It's going to be permanently saved. It'll be loaded the next time we launch the program. We can change the view, we can tip the angle, zoom in and out to see where that orbit and the current planet is compared with other planets. I see we didn't quite get it all the way down to the bottom of its orbit. We can display or turn off the orbit representation and the planet's name just like any other planet. It will also be displayed in all views of Tidewater Planetarium. So here's Planet X, well below this purple representation of the ecliptic plane, much farther off the ecliptic plane than any of the true planets. So as the simulation progresses and the planet's position changes relative to the Earth and the Sun and the other planets, its brightness will be adjusted appropriately for its characteristics. Its position will be displayed correctly in all of the views. That concludes our demonstration of this feature of Tidewater Planetarium.